Okay, so good morning, everybody. Welcome to the Center for Theoretical and Computational Physics weekly seminar. Today, it is a pleasure to welcome Daniel de las Heras from the University of Bayreuth in Germany. Daniel is actually an old friend of ours. After a PhD at the Universidad Autónoma de Madrid, he did a postdoc with us for a few years, after which he moved to Germany, where he has been since and been very successful at a lot of great work that he's been doing. And today he's kindly agreed to tell us about his work on sedimentation of colloids. So this talk is being recorded, so by staying on, you're giving consent to your image and voice being recorded and stored. And in the interests of internet stability, I ask everybody to mute their microphones and turn off their cameras during the seminar. Of course, if you want to ask a question, you can unmute yourselves and even switch on your camera if you like. And now I hand over to Dani for his seminar. Dani, please.
Oh, thank you, Pablo, for the introduction and also for organizing this seminar. So yes, I'm going to talk about sedimentation of colloidal mixtures in general, right? So the idea is how to move from the bulk phase diagram of a mixture to the sedimentation behavior of a mixture. But I will focus on a particular case, which is a mixture of plates and rods. So this is work done in collaboration with Tobias Ecke and with Matthias Smith. We are all working here at the University of Bayreuth. So what is the general system is we have two different types of colloidal particles in a given solvent, and then we mix them. So we create an homogeneous mixture. We put this in a test tube, and then we wait. And we wait, typically we have to wait a lot, but at some point, if we are lucky, then the system will reach the sedimentation diffusion equilibrium, and then we will see something like this. We will see the presence of different stacks of different thermodynamic phases. Okay, so each letter here corresponds to a different thermodynamic phase. It can be a liquid, can be a crystal, or can be a liquid crystalline state, a nematic, a columnar, etc. Yeah? So for you to have something concrete in mind, let me show you some experimental results. So this is experiments done in Bristol. So this is a mixture of platelets. The platelets are here the big particles, and spheres, the small particles. Yeah? And then we prepare here 3 different samples with the same concentration of spheres and different concentration of platelets. So this is the initial stage, which is homogeneous. And then you wait 12 hours and you see that the stacking sequence appears. So in this case, there is a bottom nematic, this yellow region where the platelets are oriented along the same direction. There is orientational order, and there is a top isotropic state. And then you let the system evolve. This is 5 months, 20 months, and then more or less after 20 months, the system has equilibrated. So the thicknesses of the relative thicknesses of each of the stacks is no longer changed. Yeah? And gravity can have a very strong effect. And to give you a first example of this, let me show you now the same results, but with the difference that the spheres are bigger. In the first case, the spheres are 30 nanometers and diameter, and in the second case, the diameter of the spheres is 74 nanometers. That's the only difference between these two systems. But as you can see, the final stacking sequence that needs up to 20 months to really find the sedimentation diffusion equilibrium. And in all cases, the sequence has changed from top isotropic bottom nematic to what we call a floating nematic phase. So there is a top isotropic, there is a middle nematic, and there is a bottom isotropic. Yeah? Although the bulk phase diagram of both mixtures is qualitatively the same, but the stacking sequences are different. Yeah? So this is a first example. The sample that I will consider here is this one. These are the results by Lecker-Kerker and van der Koik back in 1999. This is a mixture. It's a more complex mixture where both species are anisotropic. So we have rods. You can see here the rods and platelets. Okay, so both can form liquid crystalline states. And then you mix this, and then you wait, and then you find stacking sequences like this one, where there is a bottom nematic phase, which is rich in platelets. Then there is a middle nematic phase, which is rich in rods. And on top, you have an isotropic stack. Okay, and this is just for a given initial condition of the mixture. Right? But if you now change the initial condition, then you find other stacking sequences, like, for example, this one that is top isotropic bottom nematic of rods, or you can have top isotropic bottom nematic of platelets, or you can have even much more complex sequences if you consider also phases with positional order. And then, as I said, this is changing the initial condition. What does it mean? Well, if you go to the literature, then you will see that typically changing the initial conditions means changing the composition, so the relative number of rods and platelets, and also changing the packing fraction of the colloidal particles, right? The total packing fraction of the how many colloids do you have in total there? Yeah, this is what people typically understand by changing the initial conditions. One of the messages that I want to transmit here, I will try to convince you that the height, which is typically not considered in these experiments, but the height is actually also very important. Yeah? If you look at the height of these samples, you see the white lines here now are the position of the meniscus of the samples, and you see that all samples have different heights, and I will try to convince you that this is very, very important. Okay, so then first thing we need to understand is why if we start with a homogeneous mixture like this one, and then we wait long enough, then we end with something like this. And there are two reasons. So the first reason is of course the bulk phenomenology. Okay, these colloidal particles, they will phase separate in bulk. This is one reason. And then there is a second reason, which is as important as this one, which is gravity. These experiments are performed under a gravitational field, and a gravitational field is super important in colloidal systems. If you want to have an idea, to estimate how important gravity is in your system, you can calculate gravitational length, which is the ratio between kVt and the Bouillon mass of the colloidal particles times the gravity. This is a length that tells you how important, at which length scale gravity is important. Yeah? And if you do this in a molecular system, you calculate this gravitational length for water or whatever, and then you will see that this gravitational length is of the order of hundreds of meters or even kilometers. So this means that gravity has zero effect in a test tube. Yeah? But if you calculate what the gravitational length is in a colloidal system, you will see that it's of the order of millimeters or centimeters. Yeah? So this means that gravity will affect the system at length scales that are smaller or comparable to your experiment. So there's no way around. You have to incorporate gravity if you want to describe this system theoretically. So how do you incorporate gravity? This is then the next question. And what we do that seems to work very well is the following. So we consider the ground potential. The ground potential is the free energy, and then we have a sum over the species times the integral from the bottom to the top of the sample of the density profile of each species times the external potential minus the chemical potential. Yeah, this is just thermodynamics. And then the external potential in our case is a gravitational field. So it's the Bouillon mass of species I times acceleration of gravity times the vertical coordinate set. So the only thing that we do is two things. First, we group this term here. We define what we call a local chemical potential, mu1 and mu2 of Z, a local chemical potential for each species, which is the bulk chemical potential minus the gravitational field for each species. Yeah? And then it comes the approximation. We say that at each position set, we can describe our inhomogeneous sample. We can describe it by an equilibrium homogeneous system with a chemical potential that is given by this local chemical potential. Yeah? This is the approximation that we do. It's a local density approximation that in a colloidal system is very, very good in general. Yeah? So we have these two equations for the local chemical potentials that now we can group to eliminate the vertical coordinate set, and then we end with what we call, sorry, this is not working. With what we call the sedimentation path. Yeah, this tells me how the chemical potential of species 2 varies as a function of the chemical potential of species 1 along the sample. Yeah? And you see that this is simple as straight line. So this is proportional to mu1, and this is the proportionality constant, which is the ratio between the Boolean masses. Yeah? I will explain what this means later. And then we have some constant. And this sedimentation path, although maybe looks like a complex mathematical object, but when you represent this graphically, then you immediately see what the relation between the sedimentation path and the stacking sequence under gravity is. So let me show you this. We have, remember, we have a test tube of a given height, h, that will determine the length of the sedimentation path in the plane of chemical potential. And then we have some bulk phase diagram. Yeah, this is the bulk phase diagram of the mixture without gravity. Yeah, this is chemical potential of species 2 versus chemical potential of species 1. I have just made up this phase diagram. Right? I have just drawn a line which is physical, in the sense has physical properties, but I have just invented this line. So there is a coexistence between two phases, A and B, along this binodal line, and then it ends at a critical point there. Yeah? And now I can plot here a sedimentation path, and a sedimentation path in this plane is, according to this equation, is simply a segment of a line. Yeah? It's something like this, where the slope is given by the ratio between the Boolean masses, m2 over m1. Yeah? And the position is given by this complex object, which is in the end just a function of the packing fractions of the colloidal particles. Then the direction from bottom to top of the sample is given by this arrow and is given by the sign of the Boolean masses. And as you can see, each point here corresponds to some position in the path, right? This is the bottom and this is the top. And then you can immediately read out the stacking sequence, because every time the path crosses a binodal, like for example, in this point here, then an interface will appear in the vessel. Yeah? So the stacking sequence corresponding to this path is bottom B and top A. It's something like this. Okay. So then, if you want to understand what different stacking sequences you can find under gravity, what you have to do is to group all these possible stacking sequences in some kind of diagram. Yeah? We call this the stacking diagram, and there are different representations of the stacking diagram. One that is relevant for the experiment is to fix the slope of the path. Yeah? Like this one, the slope is going to be fixed now, and I also fix the height of the samples, which determines the length of this path. Okay, and then I represent the possible stacking sequences in a plane, which is the average chemical potential along the path of species 2 versus the average chemical potential along the path of species 1. Okay, so one point here represents one path there. Yeah? And then what I have to do is to look at the paths in bulk that are a boundary between two different stacking sequences. And there are a few of them. For example, the paths that start at a binodal. This path starts at a binodal, and it is a boundary between two stacking sequences, because if I move this path a little bit down, the sequence will change from A to AB. Yeah? So this path here is represented by one point there, And all the paths that start at the binodal, they form in the stacking diagram, they form this line there, yeah? That we call a sedimentation binodal. Doesn't matter. Then we also have the path that is, instead of starting, they end at the binodal. They are also special paths because they are a boundary between two stacking sequences. All these paths, they form this line in the stacking diagram. Still, we have other types of paths, the ones that cross the critical point. They are special. If I move this up, I have a sequence AB. If I move this down, I have a sequence B. Yeah? And all these paths, they form a line in the stacking diagram, this line here that we call a terminal line. Yeah? And finally, in this example, the path has a slope that is compatible with the slope of the binodal. So there are paths that are tangent to the binodal. They are also special because if I move this path down, I will find a sequence which is ABA. Yeah? All the paths that are tangent to the binodal, they are in the stacking diagram, they are along this line. And that's the stacking diagram of my sample. All I have to do now is to give names to all the regions. So how do I do this? Well, I simply select one point in each region. For example, this one. I represent this point in bulk and I read the sequence. So this is ABA, yeah, ABA. I do the same with the other regions, and then I end with my stacking diagram for finite height samples, okay? So, as I said, this is just a model phase diagram, which doesn't correspond to any real system. So let's now repeat this, but for the system that we are interested in. No? Remember this mixture of rods and platelets. So the first thing we need to do is to model the particles. Of course, there is polydispersity, charges, but we just model the particles with a very simple particle model, which in this case is rods of different lengths and diameters, such that we match the dimensions of the particles that they report in the experiments. Okay, this is our particle model, and they are hard, so they cannot penetrate each other. They cannot overlap. Yeah? And then we also need some theory to describe the bulk phase diagram. What we have done is density functional theory. So in density functional theory, you split the free energy into the ideal term, which is given exactly, and then an excess term that contains all the interactions, and then you need some approximation for this. We have used almost the simplest possible one, which is an Onsager approximation that was first for this system. It was first used by Varga and co-workers. So in essence, this just approximates the excess free energy by is proportional to the excluded volume between two particles. So the excluded volume between two particles is the volume excluded to one particle due to the presence of the other particle. Okay, and the excluded volume is lower if the particles are parallel to each other than if they are perpendicular to each other. Okay, so then what happens is that if the density of the colloids is small, then the ideal free energy dominates, and the system wants to maximize the ideal entropy, and then the system is in an isotropic state where particles are randomly distributed. But now if the density increases, then the excess free energy dominates. The system wants to minimize the excess free energy, and in order to minimize the excess free energy, what the system does is to orient themselves with the particles aligned along a given direction, which is known as the director. Okay, so if you want details about the theory, I can give you, but this is a standard approximation used in density functional for anisotropic particles. So then we minimize our functional in bulk. This is bulk, no gravity, and this is what we find. So this is the chemical potential of the platelets versus the chemical potential of the rods. Yeah, and you see there are three different states. So at low chemical potentials, you can think low densities, there is an isotropic state. Then we increase the chemical potential of platelets, and then there is a transition to a nematic rich in platelets. So something like this. All particles are oriented, all platelets are oriented along this direction, and the rods, they are perpendicular to the platelets, because this way they also minimize the excluded volume when they are perpendicular to each other. Okay. And if you increase the chemical potential of rods, then there is a transition from isotropic to anematic, which is rich in rods. And again, rods and platelets, they are perpendicular to each other. Yeah? So this is the bulk phase diagram. There is a triple point there where the three phases coexist. Yeah? And this is the bulk phase diagram in the plane of chemical potentials, which is maybe not the most relevant plane for experimentalists. So one can transform this into a phase diagram in the plane of packing fractions. This is the packing fraction of the platelets versus the packing fraction of the rods. Yeah? The binodals are the black lines, and the gray area is the phase separation region. So if you initialize your system here, it will phase separate. Yeah? And I can still specify regions within this the mixing region. For example, I can plot here the tie lines that show me which points are coexisting. These are the tie lines of the triple point. Yeah? This means that inside this region, if I initialize a system with this packing fraction, for example, it will phase separate into three different homogeneous phases: isotropic, nematic of platelets, and nematic of rods. Yeah? In bulk, yeah? No gravity. So we are in the middle of nowhere in the space. Yeah? And the same that I can also do similar things for the other regions, and then I end with these different regions in bulk. For example, a state here could phase separate in two homogeneous nematic phases, one rich in platelets and one rich in rods. Yeah? And now let's see what happens under gravity. So I first fix the slope of the path using again the experimental data. So you just calculate what the mass density of what the Bourgeois masses of the platelets and of the rods are, and with this you can calculate the slope of the path, which happens to be around 3 for the data that they report. Yeah? And now we need to fix a length. So we start with this length of the path that corresponds to a height of 5 millimeters. Okay. And we find the stacking diagram, again, in the plane of average chemical potentials along this path. So we have, in bulk, we have 3 binodals. So this means that we have 6 sedimentation binodals in the stacking diagram. And in bulk, we have a triple point there, which creates also a terminal line, yeah? Because all the paths that cross the triple point, they are special. If you move the path, the sequence changes. And then you see that there are, how many? 1, 2, 3, 4, 5, 7 different stacking sequences. So this is promising because these are the same stacking sequences that they observe in the experiment. So it looks good. Still, we cannot compare with experiments because this is the plane of chemical potentials and they report packing fractions, right? But as we have done before, we can transform this into a more relevant plane of average colloidal packing fraction in the sample. All we have to do is to integrate the density profile along the path, yeah? And then average. And this will give us what the average colloidal packing fraction is in the sample. Yeah? So this can be done. And this is the result. This is the stacking diagram in the plane of packing fractions for a height of 5 millimeters. Yeah? We can now repeat the same for a different height, let's say 18 millimeters. And again, plane of chemical potentials and plane of packing fractions. Yeah? And then you see in this case, the topology has not changed. So the topology is the same for both heights, but the relative size of each of the regions of the stacking diagrams, it has changed. Okay, we will see cases later where also the topology changes. But this already tells you that one cannot compare samples with different heights. So if you for example, have a closer look here, you can find samples where the only difference is the height. Yeah, these 2 points, they have the same colloidal concentrations. Okay, the only difference is the height of the sample, and the stacking sequence is different. So for example, here is a pure nematic of platelets, and here is a top isotropic bottom nematic of platelets, yeah? Which maybe is not so impressive, but there are even more interesting cases, like these two samples here. In this case, we have a top isotropic bottom nematic of platelets, and now I change the height, keeping the concentration of colloids constant. And then what happens is that a middle nematic of rods appears in the sequence. Yeah? So it's a total, I would say, a non-trivial change of the stacking sequence. So this should already tell you that one cannot compare samples with different heights in the same diagram. Yeah? But we will see other cases later. So then, now that we have our model with gravity, we can try to make a quantitative comparison with the experiments. Yeah. So in particular, there are 3 samples that involve only phases with orientational order, and what we can do is to find the path in the bulk phase diagram that corresponds to this sample. We know the slope. We know the height because we can measure it with a rule in the pictures that they report, and then all we have to do is to find the location of the path such that the density of the sample is the density that they report experimentally. Yeah, this is not trivial to do. You have to solve a system of nonlinear equations, but it can be done. Yeah? And in the end, we find a path, and we can plot the density profiles, and this is the density profiles has a function of the vertical coordinate, and uniaxial order parameter profile has a function of the vertical coordinate, right? So you see on top we have an isotropic state, uniaxial order parameter is 0, and on the bottom of the sample we have a nematic which is rich in platelets, and you see that the uniaxial order parameter is positive for the platelets and negative for the rods. So this means that they are perpendicularly oriented to each other. So this is our prediction. Yeah, and this is the experiment. So in this case, the agreement is perfect. It's not only the sequence; we are able to reproduce the relative thickness of each of the stacks. Yeah? This is the first part. This is the second sample that they report is this path here. Note that the length is different because the height is different. And what our theory predicts is a top isotropic, middle nematic of rods, and bottom nematic of platelets, which is the same sequence that they obtain. In this case, the theory overestimates the height of, or the thickness of the middle nematic phase, which I think is a minor problem. I mean, this is a super complex soft matter system with polydispersity, charges, maybe, and many other things. And we are using a toy model for bulk, right? So I would say the agreement is excellent. And then there is still another sample, this sample here, number 3, where the experiments are top isotropic, bottom nematic of rods. We are able to reproduce the top isotropic, then we have also the nematic of rods at the same position, and the theory still predicts a super thin stack of a nematic ridge of platelets here at the bottom that experimentally doesn't appear. This discrepancies again is because probably because we are using a toy model, and also because we are neglecting the interaction with the bottom of the sample, and also we are neglecting interfacial effects. So I still find this agreement very good, even though this super thin stack appears at the bottom. Okay. So what else can we do with the experimental data? I have now shown you how you can go from the bulk phase diagram theoretically to the stacking diagram, yeah? to the behavior and the gravity. Yeah? But you can also do the opposite thing. You can try to infer how the topology of the bulk phase diagram has to be by looking at experimental results. Yeah? And to do this, we have focused on these other 4 stacking sequences, which are way more complex. For example, look at this one. This is a stacking sequence where there is a nematic of platelets, there is a nematic of rods, there is an isotropic state as before, but there are also a bottom columnar phase, which is rich in platelets, and there is a middle what they call an X phase, which is likely a symmetric phase, and it is rich in rods. Yeah? So then one thing that we could do is to incorporate phases with positional order, symmetric and columnar. So the columnar phase has positional order in 2 dimensions. The symmetric phase has positional order in 1 dimension, the particle form layers. So this is one thing that we could do. We could incorporate these phases in our theoretical model and then try to repeat the calculation that I have shown you before. But this is, well, first, we don't want to do this, and because we want to do the opposite, the inverse problem. And second, this is very problematic because the particles are highly polydispersed. Okay? And the polydispersity, while it will have little effect in the isotropic and nematic transitions, but it will have a huge effect in phases with positional order. Okay? So instead of this, what we have done is to try to understand what the topology of the bulk phase diagram needs to be in order to reproduce the stacking sequences. Okay, so this is again our bulk phase diagram. I first make a zoom here in the region of the triple point, and then we ask ourselves, okay, what binodals, new binodals, and do I need, and what is the position of these new binodals in order to be able to reproduce the stacking sequences? And then we end with this answer. We need 2 new binodals, one between the anematic of platelets and the columnar phase, and another binodal between the nematic of rods and the X phase. And this is, we approximate this by straight lines. This is a crude approximation, but the order needs to be like this. Okay, we cannot interchange the order of these binodals because otherwise we couldn't recover the stacking sequences. So we are able to understand what the topology in bulk needs to be, and assuming, or with these binodals here, and knowing the slope and the height and the length of the path, which is given by the height of the samples, we are able to find sedimentation paths that recover exactly all the different stacking sequences observed experimentally. Okay, we are able to recover the stacking sequences, and also the thicknesses of the relative thicknesses of each of the layers is also in good agreement. Okay, and this, by the way, this reminds me something. If you look at this sample number 2, it has 1, 2, 3, 4, and 5 different stacks. Okay, and of course they don't coexist in bulk. This is not, if you observe 5 different stacks in bulk, this doesn't mean that if you observe 5 different stacks in sedimentation, this doesn't mean that there are 5 phases coexisting in bulk. This isn't true. Yeah, this is because in what you have in bulk is a straight line, is a sedimentation path. It's not a point. Yeah? Okay. So you see in our bulk phase diagram, there is only one triple, well, there are several triple points, but there are points where 3 phases coexist. There is not a single point where more than 3 phases coexist. And you find stacking sequences with 5 different stacks, okay? So then we are able to reproduce the experimental results, but still there is something here that is slightly disappointing. Yeah? And is the following. I have been telling you, and this is true, that bulk, oops, sorry. This is bulk, right? And this here, this is sedimentation, okay? And I have been telling you, and it's true, that bulk is different than sedimentation. Yeah? But if you look at these two phase diagrams, they have the same topology. There is a one-to-one correspondence between each of the regions of this phase diagram. Okay, although the meaning is totally different, because, for example, if I look here, this is a phase where anematic of platelets and anematic of rods, they mix between 2 homogeneous phases. Yeah? And this, I also have the same letters, nematic of rods and nematic of platelets, but the meaning is different. This is a top nematic of rods, bottom nematic of platelets, so the order is important, and the phases, the stacks are inhomogeneous. The density profiles, they change with the vertical coordinate. So the meaning is different, but still the topology looks the same. So one can say, well, okay, yeah, they are different, but the diagrams are quite similar. One looks like the color version of the other one, right? But this is just an unfortunate coincidence because of the slope that the path has. I will show you now that this is not true in general. How can we see this? What we can do is to play with the slope of the path. So remember, the slope of the path S is given by the ratio between the buoyant masses. Okay, and the slope of the path doesn't play any role in bulk. No, doesn't matter what the slope of the path is. The bulk phase diagram is the same. But this isn't true with the stacking diagram. You can play with the slope of the path. You can change it. This is possible by changing the solvent, for example, or by changing the inner core of the colloidal particles, by changing the material of the inner core of the colloidal particles. So it's possible. So let's see what happens if I change the slope of the path. And if you look at this paper here, we analyze how you can construct a stacking diagram that where one of the variables is precisely the slope of the path, and you can see all the different stacking sequences that they appear. So this is what we have done, and looking at this stacking diagram, we have selected one new slope, which is 0.5. So remember, before the slope was 3. Now what happens if I select a slope of the path which is 0.5? So this corresponds to the platelets being lighter than before, or the rods being heavier than before. Okay, so and then you can see here that new stacking sequences will appear, because now I can, with this slope, my path is able, for example, to cross the binodal twice and form a floating isotropic state. Or there will be another interesting sequence like this one, for example. And this sequence there, if you look at the profiles, they look like this. So on top we have a nematic of platelets, rich in platelets. Then there is an isotropic state in the middle, and then near the bottom of the sample, near the bottom of the sample, we have we have a nematic which is rich in rods. Okay. So then let's now repeat the calculation that we have done for the stacking diagram, but for this new slope, yeah, 0.5. And showing you here again the bulk phase diagram of the mixture. And now I repeat the calculation of the stacking diagram for a slope with 0.5, and this is the result. And now you can see that the topology is no longer the same. There are way more different regions in the stacking diagram than in the bulk phase diagram. In particular, you can find, for example, the sequence isotropic nematic of platelets there, and also the inverse sequence nematic of platelets isotropic. Yeah? And this is the sequence that we have been discussing before. There's a middle isotropic state. And even more interesting, if you now change the height of the sample, then the topology of the stacking diagram also changes, because there is a new stacking sequence there. I can make a zoom there, and you see that this is a sequence. If I plot a path in this small region, this is a path like this one. It's a path that starts at the isotropic. This is top isotropic, followed by nematic of platelets, then again isotropic, and then nematic of rods. Yeah, which you can then understand or see another important consequence of the sedimentation path. That is that the same stack, in this case isotropic, the same stack can re-enter the sequence. Okay, and this doesn't mean that there is, for example, an isotropic demixing in bulk. No, it's not. It's just the path that is entering the isotropic region twice. Okay. So then, I hope that this now is much clearer than before. So bulk is completely different to the stacking diagram. Yeah. Okay, this is the first important message, and the second one was again that the height is important. So to visualize this better, I'm showing you here a new representation of a diagram. In this case, I'm plotting in the x-axis. This is the height of the sample, and then in the vertical axis, I have the position set of my sample. Yeah? And what I represent is what is the stable stack at position set if the height of the sample is h. Yeah? And then you see, for example, if the height is 47 millimeters, and by the way, this is at constant packing fractions, okay? So I only change the height of the sample. So if the height of the sample is 47 millimeters, then I have a bottom isotropic and top nematic of platelets. No? Now, if I increase the height, keeping constant the packing fraction of colloids, and then we have 51 millimeters, then the sequence completely changes. There is a bottom nematic of rods and a top isotropic that appear there. Okay. And if I keep increasing the height of the sample to 55 millimeters, then what happens is that the nematic of platelet that was there in the middle, it disappears. Yeah? And the sequence is top isotropic, bottom nematic of rod. So you have quite a complex evolution of the stacking sequences by simply changing the height of the sample. Yeah? So this is the second message of this talk. Height is very important, and one cannot compare samples that have different heights in general. And I think with this I finish. So thank you for your attention, and also thank you for the funding. Yeah, this project is funded partially by the FK. So that's all. If you have questions, then yeah. Go ahead.
Okay, thanks very much, Danny, for an exciting seminar. Question session is now open, so if you wish to ask a question, please raise the little blue hand. If you don't know how to raise the little blue hand, just unmute yourself and ask your question. Don't forget to unmute yourselves.
There are no longer blue hands. I mean, the new version of Zoom, it's a yellow hand.
Mine is still blue, I'm afraid.
Because you haven't changed your software.
No, I'm a conservative sort of person.
Yeah, well, anyway.
Okay, ask your question, Margarida. Margarida, you can unmute yourself and ask your question, please.
I'm unmuted, but apparently lots of people did. First of all, apologies for getting in a few minutes later. And Danny, thank you. It was a nice, interesting talk. It's complicated, but it's interesting. And your introduction was very good. I don't understand, and can you tell me, what is the reason to believe that you can represent everything in terms of an average chemical potential? And what sort of average is it? Is just it's a weighted average or what? And why should you expect the average chemical potential to be a good field?
Yes, well, this is, I mean, it's just a mathematical representation of the stacking diagram by a point. I'm trying to go back to this. You can use any other point of the path to represent this, right? So the crucial approximation is that we say that at each vertical position of our sample, the state of the can be well represented by a equilibrium system. Yeah, this is the approximation. It's the critical point. Now, how I represent the path? Well, I'm using the middle point, which is the average chemical potential, but I could use any point, so any other variable. It's just a mathematical way to transform this path into a point. But the really relevant thing is one.
Yeah, that I understand. So the lines would probably change slope or something, but the topology would not change if you picked any other point?
Yes, exactly. The numbers will change, but the topology would remain the same, yes.
Thank you. Very, very, very clear.
And the important thing, or the relevant thing, is to then transform.
Yeah. Now I'm clear. I was just not sure what it meant, if it meant anything special or if
no. Okay.
Yeah, okay. Just a label.
Yes, it's just a label. Yes.
You need to pick one number between the two extremes and so on.
Yeah.
Okay, thanks.
Okay, thank you. Next up is Maria.
Oh, thank you, Dani, for your seminar. And then, so I have two questions. One is, so you say that everything depends on the age of your sample, and then you give numbers to the age. So in real units, I mean.
Yeah.
So, but I understand that because you are comparing with experiments. But I mean, what is the natural length? So how is defined the natural length? So is the gravitational length? So if you wanted to rescale this length to have the same results, what should you use? It's the gravitational length that you introduced at the beginning.
Well, not sure I understand the question. I mean, we use real numbers because we actually have real numbers.
No, I know that. So of course, but I mean, you have a length, and so if you do a theory, you should be able to do everything out of
okay.
the.
Okay. So the length scale that we use in our theory is simply one of the particle dimensions. I don't remember which one. Either the diameter or the length of one of the rods. This is the intrinsic natural length scale that we use in our theory, and then we transform this to the experimental length scale. But if you mean what is the relevant length scale in your system, then of course there is with the gravitational length is super relevant because it tells you how important gravity will be in your system, and then the other lengths that are important are the internal correlation length of your bulk system.
Yes, but I mean, it should be, this age should be related with the gravity. So if you put gravity equal to 0, this length is irrelevant. So
yeah, you are in bulk, sure.
Yeah, you are in bulk again, so that doesn't matter the age of the sample.
Yes, the path is a point. If you do gravity to 0, then the path is a point.
It's a point. Yeah, so that means that this length, this age, must be related to gravity somehow, to the value of gravity.
Okay, I don't know the age in combination with the value of g. These two things determine the length of this path. It's both. Yeah? So if you increase the height, keeping the g constant, then this path, the length of this path, increases in the plane of chemical potentials. And if you can also decrease gravity, keeping the height constant, and then the path also decreases. So it's both. It's the value of gravity and the height that determine the length of this path. Okay. You transform this length, the actual height of the sample, you transform it into a length in this plane of chemical potential, which is in units of kBT.
Okay.
Not sure if this answers the question.
Well, I'm not sure if I could do the proper question, but okay, thank you.
Yeah.
Okay.
Right, thank you. Any more questions, please? I don't see any more.
I can ask, Paul.
Yeah, go ahead.
It's just a general question. So we have just understood correctly. To construct stacking diagram, is it just a translation of bulk diagram in some direction? Can I think like this? To construct stacking diagram, just to take bulk diagram and just to translate it in plane, or it's not like that? Because if I look on the stacking diagram to the right now, I see that it's just translated, and if I bring, it's like line shifted in the upper left, or it's just coincidence?
This, you mean from this to the stacking diagram?
Yes.
Yeah, you can go. Well, there are there are several types of lines. This one here, the solid lines, these are just a translation, yes, of the bulk binodals, because these lines they correspond to paths that start or end at the binodal. So this, yes, but the other ones are not. The other ones they are because of paths cross the critical point or path that are tangent to the binodal. So they are not simply translations of the binodals.
Okay.
So they are all these lines, they correspond to the special paths where at least two different sequences coexist, let's say. Yeah. And you can easily go from this to this. This is easy. The other way around, well, experimentally is difficult. And mathematically, if you have the stacking diagram in the plane of chemical potentials, you can do it, but experimentally you don't get this stacking diagram. Experimentally, you can get a stacking diagram. If you do it properly, you could get a stacking diagram in the plane of packing fractions. If you do it properly with the same height for all samples.
Okay, thanks.
Right, thank you, Miko. Any more questions? I don't see any more
No, I
raised
have another
hands.
one.
Okay.
Sorry, Daniel, do you have any idea how to model these times of equilibration of this? It has nothing to do with your seminar, but so you said that these samples take a lot of time to equilibrate. Are there some models or some theories that predict the time it takes to equilibrate this, depending on diffusion coefficient, sizes of particles, shapes, or?
You mean if you want to predict what is the time?
What is the time that it takes to?
Yeah, I mean one possibility that what I would do if I had to do something like this is to use dynamical density functional theory or a power functional theory acting on the density functional that we use for bulk. Yeah? So you can start with an homogeneous system with two densities, and then use dynamical density functional theory or power functional if you want to go each on the adiabatic approximation to model the dynamics of this. And then this will give you some time scale that again you have to transform to your experimental relevant units, using in the end, yes, the diffusion coefficient, the actual diffusion coefficient of your system that you might know. But in principle, this is should be doable. Yes.
Okay. And another question. Sorry, Paul. Can I make another question?
Yeah, go ahead.
Yeah. So you at the beginning, you said that you have your two colloids in two solvents, and then you mix.
Yes.
The role of the solvent is important or not? Is it important, the role of the solvent? So if you have two different solvents, for instance.
Yes. Yes.
Then,
well, yes and no. I mean, not for bulk. For bulk, it would be irrelevant but for the sedimentation, yes, it is, because the slope of the path is given by the ratio between the Buoyan masses.
Yes.
And then the Buoyan masses, they involve the mass of the solvent. So if because it's the you have to subtract.
I know. Yeah.
But then if the colloidal particles, if they are made of different materials, let's imagine one, then this means that you can change the slope by changing the solvent.
Yes. So that's why if the two solvents do not mix, then this will be much more complicated, in the sense that you could have each particle could have several buoyant masses in the same sample, or is this possible? Or?
Well, I don't know what to do. I mean, we are assuming this assumes that there is a single solvent and these particles they mix in the solvent. Yeah, but
and that's what happens in the experiments. You don't know.
Yes, no. In the experiment they use a single solvent. Typically, these colloidal particles they are diluted in either water or toluene.
Okay.
I mean, experimentally, theoretically, you change the solvent and that's it. But experimentally, of course, this is difficult because it changes the chemistry, and then it will also change the effective interaction between particles and so on. So, experimentally, this is not just just put another solvent. I guess.
Okay. Thank you, then.
Right. Thanks. So, any more questions? I don't see any more raised hands. So let's wrap up for today. Thanks to Danny for his seminar. Thanks to all for coming. And we'll be back next week. So bye. See you then.
Bye bye.
Thank you.
Bye bye.
Ui, Daniel, tens que vir cá uma vez. Assim que isto melhorar. Where are you? You gone? No.
No, estoy aquí.
Não vieste, efetivamente. Nós estamos a viver este mundo estranho.
Sí.
Mas enfim, algum dia há de passar, algum dia. Olha, os meninos, estão bons?
También, sí, no.